So now let's take a look at example 1 to see how exactly we might be able to use the theorem that we talked about in the last video to go ahead and determine where a function actually is increasing or decreasing, again, without ever looking at its actual graph. So let's go ahead and see what we have here in example number 1. I want to determine on what intervals this function is increasing or decreasing. So according to the above theorem, as long as my function is nice and continuous and differentiable, then I should be able to figure this out. And I do have, again, a nice continuous differentiable function here because it's a simple polynomial. Now, if I want to go ahead and determine where it's going up and going down, increasing and decreasing, I have to look at the derivative. So let's start by calculating that derivative. So I'll state here that we calculate that f prime of x is equal to 3x squared plus 6x. Now, of course, I'm going to have to go ahead here and try to pull on some ideas that we talked about back in the skills check associated with this unit. You might recall that in the skills check, we were interested in solving different polynomial or rational inequalities. That is, when did a function spit out positive or negative values? And notice that's exactly what we're attempting to do here. I have a function that looks like this, my derivative function, and I'm interested now in when it's going to spit out positive and negative values. So to figure that out, I'm going to go ahead and try to find the critical points for my function. That is, where does the first derivative equal 0, and where is it going to be undefined? So notice I'll say here that first, my f prime of x will be equal to 0 when 3x squared plus 6x will be equal to 0. I can simplify this and solve this a bit more easily by taking out a common factor between these terms. Notice this would leave me with an x plus a 2, and so I can very, very clearly see that I'm going to get a result of 0 whenever x is the value of 0, or if x is the value of negative 2. So now that I have this, I can go ahead and I can check when is my first derivative going to be undefined. And of course, the answer to that is that it is never going to be undefined. So the only critical points that I have are 0 and negative 2. And you may recall again that in our skills check, we took these numbers and we put them on a number line. So here would be negative 2 and here's 0. Again, these are my x values, and here are the values of my derivative. Obviously, I know that these guys here spit out 0 for the derivative. And now, just like in the skills check, I can go ahead and test values of the derivative in these intervals between and to the left and right of negative 2 and 0. So let's go ahead and pick a value over here and kind of evaluate the derivative there. So let's see what we end up with. If I was to go ahead and say plug in something like negative 3 into my derivative, I could plug it in here. I could plug it in really any of these forms, whether it's factored or not. Now I'm actually going to go ahead and focus here on the factored form because I think it's a bit easier. Remember that I don't ultimately care about the value that I get back, but I care whether it's positive or negative. I care about the sign of the value. So if I was to plug in a value like negative 3, notice that this piece here would be negative, this piece here would be negative, and negative times negative would result in a positive value. So over here, my derivative spits out positive numbers. Now, if I was to pick a value between negative 2 and 0, maybe like negative 1, I could see that this is going to produce negative values, and this quantity here is going to produce a positive, meaning that the total result is negative. And now I would plug in a value bigger than 0, maybe like a positive 1. I would see that both of these quantities would be positive, which results in a positive outcome. So I'm just again testing these values inside of the derivative, and now I can see my derivative spits out positive numbers on these intervals, and it spits out negative numbers on these intervals. But like we saw in the theorem in the last video, and in the pictures before that theorem, when my derivative spits out negative values or negative slopes, the graph's decreasing, and when it spits out positive values or positive slopes, it's increasing. So I can immediately go ahead and determine that f of x is increasing on the intervals from negative infinity to negative 2, also from 0 to infinity. And then I can also state here that f of x is decreasing on the interval from -2 to 0. So I've gone ahead, I've made these claims about what the graph is doing without ever seeing the picture. That's pretty cool. Now, I can go ahead and actually double check this. If I had a calculator and I just pulled this up, you could see that I could try to go ahead and type in the function that I'm working with here. Oops, that should be a plus, so I'd have x to the third power plus a 3x squared. That was my original function. And notice that if I was to go ahead and type this in, you can see again, I'm going to have from negative infinity all the way to -2, which will be happening right here. The graph goes up. Notice from 0 to infinity, the graph also goes up, and from -2 to 0, the graph is going down. And this is exactly what we predicted right here. So this works flawlessly. I just have to remember this basic idea. Positive slopes correspond to a graph going up, and negative slopes correspond to a graph going down. Then if I can just figure out when my derivative spits out negatives and positive things, just like we did in the skills check, I'll be good to go.